Thank you everyone for joining this workshop. I'm Sumedha Swami and I'm a Principal Product Manager in the Sagemaker team. I'm joined by our Senior ML Specialist Solutions Architect, Sean Morgan. In this workshop, we will demonstrate recent integrations between Sagemaker Studio and Amazon EMR that make it really simple for data scientists and machine learning engineers to use big data frameworks such as Spark, Hive, and Presto in their machine learning workflow. Let's look at the learning objectives. This is an advanced or 300 level content. We assume some familiarity with using notebooks to run machine learning. We also assume some familiarity with data processing using Apache Spark. However, we do not expect the audience to have direct or deep experience implementing such solutions. The content in this workshop is targeted towards two personas. First, data scientists looking to simplify their machine learning workflows without having to juggle between multiple tools and interfaces. Next, administrators who are looking to simplify management of tooling by standardizing data analytics, data preparation, and machine learning tooling onto one integrated development environment. After this workshop, you will be able to understand some notable capabilities of Amazon Sagemaker Studio and Amazon EMR. You'll be able to understand the benefits of a universal notebook that you can use for data analytics, data preparation, and ML. You'll also understand how you can easily incorporate scalable big data workloads using Amazon EMR as a part of your ML workflows on Sagemaker Studio. We will deliver the content mostly through live product demonstrations. Note that this is a virtual workshop, which means you can try all of these demos yourself live. Sean will shortly provide instructions on how you can get set up to try these demos. So let's get started. First, a broad introduction to Sagemaker Studio. Amazon Sagemaker Studio is the first fully integrated development environment, IDE, for machine learning. Our customers love that Sagemaker Studio provides a single web-based visual interface where you can utilize a comprehensive set of features to address each step of the machine learning development process, including preparing data, building, training, tuning, and deploying models. Some of the notable features include elastic and shareable notebooks, and we'll talk more about this shortly. Automatic model creation to reduce the barrier for your business to benefit from machine learning. Experiment management to capture, organize, and compare every step of your model iterations. Automatic model tuning through hyperparameter optimization. A debugger that enables you to debug and profile training runs, and a model monitor to continuously monitor the quality of your production models and drift in data quality. These are just a sample of the capabilities of Sagemaker Studio. You can visit aws.amazon.com/Sagemaker for a comprehensive list of all of the capabilities offered. Let's dive a bit deeper into the capabilities of Sagemaker Studio notebooks. Notebooks are an integral part of Sagemaker Studio, powering and complementing these rich set of features to provide an easy and integrated experience for machine learning. You can start your notebook without spinning up compute resources, so you spend no time waiting for an instance to spin up just to start looking at your notebook. You can easily dial up or down available resources to match your workload, so you only pay for what you need. You can customize the environment to uniquely suit your company's needs. You can bring your own images, packages, extensions, and can also automate customizations with lifecycle configurations. SageMaker Studio makes it easy to share notebooks with your coworkers. You can share a complete snapshot of your work so that you can give and receive feedback to make quick progress on your data science work. Also, you can run end-to-end data preparation and machine learning workflows in purpose-built, performance-optimized runtimes, and we're going to dive deep into that today. Finally, administrators can manage access and permission to the fully managed and secure environment. Now, let me give a brief overview of Amazon EMR. Amazon EMR is a cloud big data platform that enables you to run petabyte-scale distributed data processing jobs using open source analytics frameworks such as Apache Spark, Hive, Presto, HBase, Flink, Hudi, and many more on AWS. Amazon EMR comes with version releases. You can easily select and use the latest open source projects on your EMR cluster. We try and update the most popular frameworks such as Spark within 30 days of release. For those of you new to Spark, Apache Spark is an open source distributed processing system used for big data workloads. It utilizes in-memory caching and optimized query execution for fast analytic queries against data of any size, large and small. Our customers use Spark for batch processing, petabyte scale data for interactive queries, for real-time analytics, for machine learning, and for graph processing. One of the coolest features of EMR is the EMR runtime for Apache Spark. This is a performance-optimized runtime environment for Apache Spark that is active by default on EMR clusters. EMR runtime for Spark can be up to 3 times faster than clusters without EMR runtime and has 100% API compatibility with standard Apache Spark. This improved performance means your workloads run faster and saves you compute costs without making any changes to your applications. Additionally, Amazon EMR clusters can utilize Graviton2-based EC2 instances. AWS Graviton processors are designed by AWS to deliver the best price performance for your cloud workloads running in Amazon EC2. With Graviton2 instances and Amazon EMR runtime for Apache Spark, you can realize up to 30% better price performance. Amazon EMR supports Ec2 Spot Instances. As a reminder, Amazon Ec2 Spot Instances let you take advantage of Ec2 capacity in the AWS cloud. Spot instances are available at up to a 90% discount compared to on-demand prices. Spot instances give you flexibility. You can choose to reduce your computation costs using spot instances, or you can choose to get faster results by increasing the throughput up to 10x while still staying in budget. Finally, on price performance, EMR charges are billed per second, so you only pay for your usage. EMR runs directly against data stored in your S3 data lake. You don't need to move that data or transform the data just to use it. Because you're running against S3, you can have multiple clusters operating on the same data. EMR decouples compute and storage, giving you the ability to scale each independently. So depending upon your workload, you can optimize your cluster for compute or for storage. For storage, you can take advantage of tiered storage of Amazon S3, and for compute, you can take advantage of EC2 Spot instances that I just spoke about. With EMR, you can easily create clusters and provision hundreds or thousands of compute instances to process data at any scale. With EMR managed scaling, your EMR clusters are automatically resized for the best resource utilization without the need to author or configure complicated scaling policies. You just specify the minimum and maximum compute limits for your cluster, and EMR automatically resizes your clusters based on continuously sampling key metrics associated with the workloads running on the clusters. With EMR managed scaling, you can save 20 to 60% of costs depending on your workload pattern. Finally, EMR continuously samples key metrics associated with the workloads running on the cluster and automatically terminates when the cluster is idle, helping you manage costs. We launched the first version of EMR in 2009, over 10 years ago, and have been constantly innovating in areas such as performance to make sure EMR is the best place for you to run Spark, Hive, Presto, and other big data workloads. Now let's talk briefly about universal notebooks. Our customers love the comprehensive, purpose-built set of ML and data prep functionality offered on Sagemaker Studio and Amazon EMR respectively. However, while some organizations see data science, data engineering, and data analytics as separate siloed functions, we're increasingly seeing with many of our customers that data preparation and analytics are foundational components of machine learning workflows. For example, although organizations have data engineering teams to clean and prepare data for analytics and ML, the specific data that a data scientist needs for training a specific model may not be available in the repository of data that data engineering teams may have prepared. Even if some of the data is available, it may not be in the required format or contain granular level of data that is needed for ML. Data scientists would therefore want to be able to analyze, visualize, and prepare data to suit their custom needs for ML. However, today, data scientists need to use different tools and different workflows to perform these tasks. Data scientists are having to spend a significant amount of time managing infrastructure, authentication, and tools that they would rather spend on being productive, preparing data, building, and optimizing models. Administrators, on the other hand, are looking for ways to standardize data analytics, data preparation, and ML tooling so that they can simplify management of these tools and more consistently apply security and access control across analytics services and ML services. To help realize this vision, we are introducing Sagemaker Studio Universal Notebooks. Sagemaker Studio now comes tightly integrated with Amazon EMR. Data scientists can therefore use Sagemaker Studio Universal Notebooks to perform their end-to-end data preparation and ML workflows without juggling between tools. I am now going to hand it off to Sean, who will show through live demos the Sagemaker Studio integration with EMR.
Thank you, Sumita. For today's virtual workshop, we're going to be running through one of the modules of our Sagemaker Studio and EMR workshop. Specifically, we'll be looking at the time series analysis module. We're going to accomplish probabilistic forecasting of electricity demand on a large-scale data set using our connectivity with a Amazon EMR cluster. We'll take our process data after we have run our analysis on the cluster, and we'll utilize a built-in SageMaker algorithm known as Deep AR in order to create our probabilistic forecasting model. If you're watching a replay of this video, you can follow along with the workshop in your own account by attending the GitHub repository here, known as AWS samples/Sagemaker Studio EMR. If you go into the workshop folder, you will notice that there is a 00 setup directory. Within this directory, we talk about the different ways in which you can follow the workshop. For those of you following along on the live stream, we will talk about Event Engine temporary accounts, which have already been pre-provisioned for you. But for those following the replay, we have provided a CloudFormation template, which will enable your Sagemaker Studio domain to utilize a pre-provisioned Amazon EMR template. You simply need to load this URL, switching the region for whatever region your Sagemaker Studio domain is in, and then supply a few bit of parameters so that the Amazon EMR cluster has connectivity to your Sagemaker Studio domain. For those of you following along in the live stream, We will now paste the event team hash into the chat. You can head over to this URL at dashboard.eventengine.run/login, and you can go ahead and paste the event hash into this web page. These accounts are pre-provisioned with the necessary resources for the workshop, so we can get started right away. After entering the event hash, you'll be brought to this page where you can utilize your email or a Amazon login, Amazon.com login, in order to generate a one-time password. For me, I'm going to go ahead and select Amazon employee, and we'll be brought to the same page. This team dashboard provides you with a graphical interface for launching a pre-provisioned AWS account with the necessary provisions. I'm going to select AWS console, where I can then be loaded into the traditional URL. Simply select Open Console on the link that opens up below. Going to make my screen a little larger. And you can see we are now in the familiar AWS console landing page. Please go ahead and select the Amazon SageMaker link below, or if it is not within your screen, you can simply click the search bar at the top and type in SageMaker. From the Amazon SageMaker landing page, you can go ahead and select Control Panel on the left side, in which you will see that a pre-provisioned Sagemaker Studio domain has been created for you, as long with a Sagemaker Studio user. I'm going to open this Launch App selector and open a Sagemaker Studio Jupyter Lab in a new tab. The first time a user launches Amazon SageMaker Studio, it will take a few minutes to load as the containers need to be pulled down for the particular user. Upon the next time that you launch it, it should be launched much quicker. While this goes ahead and provisions, I'm going to go back to the workshop and talk about the different material that exists in there. So the landing page of this GitHub repository is the SageMaker Studio EMR repository on AWS samples. You'll see a lot of information such as interactive notebooks, various CloudFormation templates that you can use as part of provisioning EMR clusters. But for today, we're going to be explicitly looking at the workshop directory. You'll notice that there are several different modules in here. As we mentioned, the setup directory is for those of you who are following along in your own account. But there are more than just the time series module that we're going to be going over for today. We have a warm-up section, which introduces a lot of the fundamentals of the connectivity between SageMaker Studio and EMR, as well as some NLP sentiment analysis modules, as well as regression modules using deep learning frameworks. As I mentioned, for today, we're going to be doing the time series analysis using a built-in SageMaker algorithm known as DeepAR, and we'll go into a bit more details about what that is shortly. Going back to my SageMaker Studio, the container has been provisioned and the Jupyter Lab server is launched, so it should only be a few more moments here before I land on the landing page. As you can see, I have now landed into a fresh SageMaker Studio IDE with the user directory. The EFS or network mount for my user is a clean slate. If at this point you're following along and are falling a bit behind, you may want to pause the video to catch up. The first thing we're going to look at here is the connectivity with Amazon EMR from SageMaker Studio. The launcher has a lot of different materials for jumpstart models, importing data, creating notebooks. But if you look on the left panel, you'll see that specifically there is a tab for what is known as SageMaker Resources. If I click the SageMaker Resources tab, I'll be presented with a dropdown for a number of different Sagemaker Studio integrations here. There are things such as projects, pipelines, model registry, but for today's virtual workshop, we're going to be specifically keying in on the clusters dropdown. You'll notice when I load the clusters tab within Jupyter Server, I can see that there is already a pre-provisioned existing cluster. We'll be using this for today's virtual lab since it is already running, but if you're following along with the self-paced lab, be sure to provision your cluster and have it running prior to starting the actual notebooks. If you're running the live version within these Event Engine accounts, still proceed with the cluster creation that I'm about to follow along with so we can get a feel for how it works. We'll note that the existing cluster that is already here has a nice drop-down button that you can select on the left side, where you can glean more information about this existing cluster. We can see that there is one master node running an M5X large and two core nodes running M5X large as well. Apache Spark 3.2 is running on this cluster, Hive 3.1.2, and Apache Livy 0.7.1. One last thing to note is that there is an account ID visible for this cluster, and the reason that is because this does support multi-account cluster support. For example, you could have clusters in one account that is being used for compute, while there would be a data scientist account where the studio domain is provisioned. I'm going to go ahead and create a cluster now to show the connectivity between SageMaker Studio and Amazon EMR by clicking this orange Create Cluster button. We'll be given a list of templates that have been pre-approved and provisioned by our DevOps team. In this example, in the accounts, you should see a SageMaker Studio domain no auth EMR template. If I click that and go ahead and click Select Template here on the bottom right, we will be able to see the parameters for which I can configure this new cluster. We're going to do a bit of a deep dive on these cluster creation templates now. As you can see, the available configurations that I'm looking at are purely the information that a end user data scientist or data engineer persona would want to utilize. Things such as cluster name, where I will go ahead and enter my new cluster. I've also been given the selection of the EMR version. I can select between EMR 6.6, the most recent as of the time of this recording with Spark 3.2, as well as an EMR 5 version, which contains a Spark 2 version running. I'm going to go ahead and keep the EMR 6 selection. I'm also given the ability to select the core instance types, as well as the master instance types and the counts of the core instances. You can see that there are pre-approved numbers for which I can select. The last configurable parameter that we see is the idle timeout. This is the number of seconds that the cluster will remain idle before it will automatically spin down. This configuration can be extremely useful for machine learning data prep, where you simply want to provision the compute that you need for the data processing and not have to worry about if you forgot to shut down the cluster. The underlying backing of these clusters for Amazon EMR are CloudFormation templates. And so in this example, we've given the end user, the data scientist or data engineer, the specific parameters for which we thought they would need to configure. Under the hood, the CloudFormation template can use any parameters that are configurable through CloudFormation. And so we can utilize things like Graviton instances or auto scaling, as Smita had mentioned before when going over Amazon EMR. From a DevOps or an administrative standpoint, I can see the underlying CloudFormation template that is provisioned in these accounts by simply going back to the AWS console and typing in the top search bar here, Service Catalog. You can see that AWS Service Catalog creates and uses standardized products, which is exactly what we're doing with our EMR templates. They are standardized products for which the end users have been authorized to provision. I can select my SageMaker product portfolio, select this template with the same name that we had selected in the prior screen, and then select a version of that product. You can see that it is currently active. And if I go ahead and select the template, I can go ahead and see that underlying CloudFormation template. The given parameters, such as the cluster name, the master instance types, the core instance types, are all available with their allowed values. Again, this is for a DevOps or admin persona to really interact with. As a end user persona, you're simply given a streamlined set of parameters that you need to utilize. We're going to go ahead and create this cluster now by clicking the orange Create Cluster button. And we will see the depending action on the cluster creation. It takes about 10 minutes to spin up this particular EMR cluster, so we'll come back to it later in the demonstration. Another thing worth calling out within the parameters that were configurable in that template was that we didn't need to note the VPC information or subnet information or security groups. That had all been handled for me by my DevOps administrator. This was designed so that end users, such as data scientists and data engineers, can focus on what really matters for their workloads. I am now going to clone the code repository that we're going to use in today's workshop, and I'll start by clicking the file browser on the left side panel. We can see that there are no directories currently on my user's EFS home directory, and so we need to clone that repository. I'm going to go back to the GitHub page where I can go ahead and select the green code box on GitHub, and I'm able to copy the HTTPS link for this Git repository. From here, I can select this Git icon on the left-hand side, right below the file picture, and I will be presented with three options. One of them to open a file browser, initialize a repository, or clone a repository. In this example, we're going to clone a repository. From here, I'm going to open this new directory that has been cloned, and I'm going to open the workshop directory of this folder. Lastly, I'm going to open 03_time series for our analysis today. You'll notice that there is one notebook within this directory, and I'm going to go ahead and open that now. When we open notebooks within Sagemaker Studio, we need to tell Sagemaker Studio what is the backing kernel that will run our notebooks. It's part of what makes Sagemaker Studio so flexible is that you can choose different images and different instance types to back any given notebook, even concurrently. For this connectivity with our Amazon EMR cluster, we're going to select the container image known as Spark Magic. So if we scroll down, we'll see that they are in alphabetical order. We will see the container known as Spark Magic. From here, we get to select two different kernels, the first one being PySpark and the second one being Spark Scala. You can use either one depending on what your preferences are. For this notebook, we'll be using PySpark. I'm going to go ahead and select Start, and we're going to start this notebook kernel. The first time for which you start a instance and kernel will be a few minutes to load up the instance. It is doing under the hood, it's spinning up that instance specifically for running this notebook. If I want to monitor my currently running kernels and instances, I can select the third tab here on the left-hand side, which will show us the running apps and instances. As you can see, we're still starting up our kernel. While it starts up, we can review the beginning introduction of our notebook. As I mentioned before, we're going to be doing a probabilistic forecasting of electricity demand using a built-in algorithm known as DeepAR. To do this, we're going to be running the Spark Magic PySpark kernel, and we're going to select a T3 medium instance shortly once the kernel has been provisioned. This notebook has been designed to run on EMR cluster with an M5X large master node and two M5X large core nodes. As we saw, that is the current setup of our existing cluster, so we should be good to go. The core task which we wish to accomplish in this notebook is preparing and processing a dataset at scale using a remote distributed Spark cluster. We're going to utilize the core nodes in order to parallelize our processing as we go about munging this data and putting it into a dataset format for which we can train our machine learning model. The dataset that we'll be using for today's demonstration was a 700 megabyte dataset of energy consumption across 370 clients over time. The dataset comes from the UCI machine learning repository and has been used in several academic papers. The format looks like the below table here. You can see that there are 15-minute increments for each client, and then a value measured in kilowatts for the demand usage over that period. Our kernel has now been provisioned. We can see at the bottom the kernel is idle. And if we go ahead and click this button down here, you can actually see the CPU usage and the memory usage of that given kernel on our instance. We can see by default, it spun up a T3 medium instance. And if you would like to change that, you can simply select this button here at the top right where it says switch instance type. There are 4 instance types for which you can choose to back any given SageMaker notebook in the fast launch pool. You can see there's the rather lightweight T3 medium instance that we'll be using for today's demo, as well as some more heavy accelerated hardware computing or memory or compute optimized instances. Because we're going to be utilizing a remote cluster, which already has that compute capacity, we can simply select the lightweight T3 medium instance. While we're in the select instance page, I will show that if you turn off the fast launch only button, you can see the full list of provisionable SageMaker instances. But as I mentioned, we're going to click cancel because we are running a T3 medium as we want to be. So let's get started with our lab. To begin, we first need to connect to that remote EMR cluster. In order to do that, we have kind of a commented out boilerplate code here. So I'm going to go ahead and select that comment and delete it. In order to generate the correct code in order to connect to the given cluster, we're going to utilize the tight integration of SageMaker Studio notebooks and EMR. You'll notice on the top right is a cluster button that you can select, and you'll be given a view of the existing clusters that are available to you. As we can see here, the cluster that we had seen previously, known as existing cluster, is available in your account. If I go ahead and click the drop-down arrow, again, I can see information for this cluster, things such as the nodes that are running, the apps and the versions that it is running, as well as a Spark history server if I wanted to look at historical applications that have ran on this cluster. There's only one cluster right now. We'll see the new one shortly, but I'm going to go ahead and select this cluster and go and select the orange connect button. We have different authentication mechanisms that are supported here. For this demonstration, we'll be using no credential, but it's important to note that Kerberos and LDAP authentication are also supported through this widget. Immediately, you'll notice that the cell has been auto-populated with the necessary information to connect this notebook to the EMR cluster. This process takes roughly 10 to 15 seconds and will be shown a widget showing our specific application information when it is complete. We can see that the connection has been made and we have now started our Spark application. We're given some information about the Yarn application ID, the kind, which is PySpark, and the state that is an idle session at the moment. One of the other advantages is that we're given a Spark UI link, which we can select as our interactive graphical view of the logs in our session. This pre-signed link enables you to simply, with one click, traverse from your Studio notebook to the much beloved Spark UI for the Apache Spark developers. You'll notice that we can see things like the event timeline where the executors and drivers have been added to our session. We can look at the stages, the storage, the environment, and the executors, and we'll do all of this as we proceed with our demo. I'm going to close this now because we're actually going to create a new application, which we'll talk about shortly. The reason we're going to create a new Spark application is because we actually want to do something rather unique in this notebook. We're going to utilize what is known as notebook scope dependencies. What these are they enable you to install Python modules or libraries onto the given nodes of your clusters without interacting with other users on the cluster. It does this by configuring your Spark session with a virtual environment for which we can install our own packages that are specific to this notebook and not have the side effects of interacting with other people's libraries. When we provision the cluster, there are a set of bootstrapping scripts that are ran, which install specific Python libraries onto the cluster already. But often we see that data scientists or data engineers need to install additional packages without wanting to re-spin up their cluster. To do this, we're going to run this Spark Magic configure command here, which enables us to provide a JSON of the available configuration changes we'd like to do. For this example, we're saying that we want to be able to use a virtual environment, but there are other configuration changes you can make, such as the executor memory or number of cores per executor. This specific kernel is utilizing the open source Spark Magic library, which builds in a lot of these really nice magical features that we'll be using throughout the day. As you can see, I have a new application ID 003, and we can go ahead with proceeding with our notebook. The first thing that I want to do is I want to check the pre-installed Python packages that were bootstrapped when we launched our cluster. I can do this by doing this Spark context.list packages. When we make a connection with Spark Magic, we're given a couple of variables known as the Spark context or the SQL context, which we'll be using in this notebook. We can see that a number of Python libraries are already pre-installed on this cluster across the different various nodes. We can see things like pandas, NumPy, matplotlib, and other standard libraries that data scientists and data engineers will often be using. However, for this particular notebook, we want to install an additional package known as PyArrow so that we can perform vectorized user-defined functions, which we'll see more of later in this session. To do this, we can simply utilize the Spark context and install a PyPy package of PyArrow. This will install the package on all of the executor nodes so that we can successfully utilize it in our processing. We can see we've successfully installed the package. I'm going to start a new cell here where I use the info magic to show the same widget that we had seen before for the various information on our Yarn application. If I click the Spark UI link again, we'll be again taken to that pre-signed link where we can utilize the Spark UI. We'll be using that Spark UI throughout the session as we go along with executing our remote cluster job. The first thing we're going to do on this notebook is utilize the local instance that is backing our notebook. It's important to understand that we are running remote calls on a cluster, but we can still utilize the underlying instance, in this case a T3 medium, that is running our particular notebook on Sagemaker Studio. We can do this for a number of reasons, and we'll see several later in the lab, but to start, we're going to be generating some boilerplate information. We're going to import the Sagemaker SDK and use it to establish what a default S3 bucket we can utilize is for saving our process data. I'm going to run this cell with the local magic at the top, which tells the Spark Magic kernel that this code is intended to be ran locally on the notebook. We can see that if I were to create a cell that says local and then to print out the variable known as bucket, that there will be a Python string associated with that variable on the local notebook. At this point, you don't need to follow along because I'm going to intentionally induce an error But if I go ahead and just write cring bucket without the local magic, this command will be executed on our remote cluster. And on that cluster, we do not currently have a bucket variable. So the next thing we're going to do is we want to pass this information that we have generated locally up to our cluster. And to do this, we'll utilize a very handy send to Spark magic. So we'll do %% send to Spark. We'll name the local variable, Python variable that we want to send up. We'll say what the type is, a Python string, and then we'll name the variable that we want it to exist on the cluster. We're going to do this for our input data location, our output data location, and the schema. Now see if I were to go ahead and print that particular variable on the cluster, because we are not using the local magic, it will now be available for usage. Now that we've passed up some necessary information to our cluster, let's utilize that cluster to prepare the data for our machine learning application. The algorithm we're going to be using today is known as Deep AR. And if we go to the SageMaker documentation, you can see there's a lot of information provided on the Deep AR forecasting algorithm. Specifically, it utilizes recurrent neural networks as well as classical forecasting methods such as ARIMA models. This particular model has a specified input and output interface for which it expects the data to be in the format of. You'll notice it's looking for JSON files with a start, target, and dynamic feature category. So we need to process our data in such a format that the model can accept this. If you're interested in more of the specifics of the Deep AR forecasting algorithm, we can go to the How Deep AR Works, where we can see that components such as frequency of various features, as well as seasonality, are all incorporated in this modeling format. In order to prepare our data at scale, we're going to utilize our Apache Spark cluster. We'll note that we're importing a number of different Python libraries here, all on the cluster because we are doing these without the local magic. So we're going to import some PySpark classes, as well as some other different methods that we'll be utilizing. We see that the libraries have been imported, and so now we want to utilize Apache Spark to read this data directly from Amazon S3. We're going to specify the separation delimiter, the header exists, we will set a timestamp format for our data, and we will point towards that S3 input data location for which we have passed the variable to the cluster. Next, we're going to cache that data for faster performance throughout our lab here. I'm going to trigger the lazy execution of that loading by running a data.show call. And at this point, we can go ahead and look at our Spark UI to see what we've been doing. If I look at this particular Spark UI, I can see that there are stages that should have started to be formed as I build the directed acyclic graph that I want Apache Spark to execute. You can see that the loading is currently running. You can monitor the duration of this running, and we'll utilize this from time to time as we move through the lab. We can also see that within the storage category, we can see this information for which we are caching, as we have just triggered that command. When we look at the data, it is in the format that we had previously expected. There are 15-minute increments for various clients and the kilowatts usage of those periods. For our particular modeling use case, we're going to resample those 15-minute intervals into 1 hour, partly to speed up the training, but also because that is the format for which we want to do our predictions. I make a Spark call to group by the various hours within the date column and do this by the clients. Next, we're going to create a dictionary to integer mapping so we can encode each client. We'll see that this collect call will trigger an execution, and we can actually monitor the progress in real time from our notebook. If I were to go to the Spark UI, I could see this in action through the Stages page as well. You can see that our task is currently running. Which matches the information we're given to the end user in the notebook. One of the nice things about distributed computing is that as this dataset size scaled up, we can simply utilize more executor nodes or auto scaling in order to perform this at scale. Now that we have the data prepared in hourly formats, let's go ahead and visualize the time series data so we can understand what this looks like over time. We'll do this by sampling 6 random clients, and we're going to go ahead and group by date and build a format that we can utilize for our plotting. The next cell that we're going to run actually generates a plot on the EMR server for which we will be able to pass that image back to the notebook using this handy matplot functionality or magic. This can be incredibly convenient if you're doing very large scale data visualization and you simply want to pass back a more manageable PNG or generated image. From this image, we can see that the electricity demand of various clients is not always uniform and doesn't always start the same date. So what we'll need to do is we need to process this data in such a format that it is ready to be utilized by our machine learning algorithm. Specifically, deep AR requires no gaps in the data. So we want to check to make sure that there is no weekly occurrence of gap data. This may be particularly useful for something like stock trading activity where we'd see like Saturdays and Sundays, and we'd have to insert NaN values into those locations. We're going to use the power of Apache Spark to do some distributed data analysis to make sure that we don't have any day of the week type gaps. And to do this, we will simply create a column known as day of the week and a pivot. And then we'll do some aggregate counts on those days of the week. We're going to specifically show the days of the week values for aggregate values for 5 clients. And then we will also show the minimum counts of observations and maximum counts of observation across those days for all clients. See the data processing. And again, we can see this through our Spark UI as well. We note that for this sampling of 5 clients, we can see that they all have collected values on every given day. And if we look at the minimum and maximum values of all of the various weekdays for all clients, that none of these have empty days. So this is great. That means the deep AR data has no gaps. We don't need to impute any NaN values or anything along those lines. So we can proceed with the training algorithm. Because this is time series data, we need to split our training and testing data set across a date axis and make sure that there is no data leakage from the testing set back into our training set. Again, we'll utilize Apache Spark for this. We'll go ahead and select a given train start and a test start date. And we will split two new data frames across the greater than or less than of that value. The next thing we want to do is we want to format this data frame into the specific format that Deep AR is looking for. Specifically, we're looking for a data frame of targets, categories, and starts. And to do this, we're going to utilize traditional pandas syntax. Depending what version of Apache Spark you're using, there are various ways to do this. In some of the most recent versions, you can actually utilize a PySpark pandas data frame. You can also utilize the pandas UDF that we'll be using here, which is compatible with Spark 2 and Spark 3. And so to do that, we're going to identify the structure for which we expect our output data frame to exist. We have a target, which is an array of doubles. We have a category, which is an integer, and a start, which is a string. So we're going to go ahead and define that output schema. And then we're going to define our pandas user defined function. We're going to apply this user defined function grouped by the clients on our training data, and then we'll quickly show what that looks like when it's complete. If you're wondering where this particular structure information came from, if we go back to the documentation, we can see the input and output interface for this particular algorithm with the starts, the targets, and then the cats. And as you can see, our data frame now matches the required format that we need to pass this data to the algorithm. It's at this point that we want to save this data to Amazon S3 so that it can be utilized for our machine learning algorithms. We're going to use this moment to call out the capability of the Studio Notebook to make configuration changes to your Spark application in real time. Specifically, I'm going to disable the file output committer that would write a _success meta file into the directory. For Deep AR, it actually doesn't matter. The algorithm will skip over that meta file, but for other machine learning applications, you may not want to have that extra file in your data processing directories. Now that the data has been prepared, we're going to write this data to the S3 bucket that we have passed to our cluster from earlier in the lab. We're going to go ahead and write this using a JSON format as expected by Deep AR, and it's going to write them as shards. The reason that we write data as shards is because in a big data ecosystem, you don't have the ability to coalesce the data all to one node. If you did, you wouldn't need to be really using distributed data processing. By writing out the various shards to our S3 bucket, the Deep AR algorithm will actually utilize all of the shards that are needed in the model training. As you can see, we can scale up the instance types of that model training for performance or for memory computation or distributed training as well. I'm going to utilize this local magic again here, and I'm going to utilize the Sagemaker SDK's ability to list S3 bucket data. There's several different ways you could do this. You could use the AWS CLI, you could use Boto 3, but seeing as we already have this module imported, I will go ahead and do that. As you can see, this data was sharded into 27 different files, and we're going to utilize all of them in our model training. To train the model, we're going to launch an ephemeral SageMaker training job from this same notebook without any need to pivot to a different kernel or anything. So what we're going to do is we're going to use the local magic because we want to utilize our local notebook in order to retrieve the container URI for the forecasting Deep AR algorithm. We're going to set a few hyperparameters here that we want to utilize in our training, particularly the prediction length, which is how long we will predict, which is going to be 1 week into the future. And we're going to look backwards at the last week of data when making those predictions. I'm going to construct a Python dictionary of the particular hyperparameters that we're going to use in our training. And if we're interested in what various hyperparameters you can set for this algorithm, we can go back again to the deep AR documentation and go to the hyperparameter page. Here you can see a thorough description and required values for all the various parameters such as epochs, prediction length, time frequency, cardinality, etc. I'm going to go ahead and kick off this training job, and then I'll describe the underlying parameters that we're feeding to it. One of the very nice things about SageMaker built-in algorithms is that you can simply provide data as well as hyperparameters and launch your model training. There's no need to provide scripts, training scripts, or things along those lines. You can simply utilize our built-in algorithms. SageMaker also supports containerized model training. We have pre-built containers such as PyTorch, TensorFlow, MXNet containers that you can simply use with your own machine learning script or .py file. Additionally, you can build your own containers if you want to use a particular machine learning framework that we don't have first-party support for. All of these methods, whether it be built-in algorithms, scripts provided to our managed containers, or your own custom container, all leverage this concept of a SageMaker Estimator, similar in the paradigm of a scikit-learn estimator that you generate and then you fit with specific data. We can see that for this job, what I did was I passed in the image URI of the deep forecasting container that we retrieved in the cell above. I said that I wanted to kick off this instance on a C5 2x large, and I wanted to pass in my various hyperparameters as well as the output S3 location for the model once it has been trained. This particular algorithm, DeepAR, you can simply increase the instance count parameter, and you'll be able to utilize distributed training across your data sets, something that is quite commonly done in this kind of deep or large data systems. Lastly, we went ahead and we fit this estimator with that S3 process data location where we had saved our Apache Spark process data. This particular job is running as an ephemeral job where you're only billed from the start of the training until the end of the training. And we can see the actual logs of this job being directly written into our notebook. This is the standard out, standard error of the container, and we'll see it as it completes. Here, we can see the actual standard out, standard error from that container. We can see the actual logs as they are written. We can see the specific train loss of this algorithm. There's a number of various metrics that are captured by this built-in algorithm, which we can talk about a little bit more in depth in a moment. We can see that there is built-in checkpoint saving. And what you can do is actually SageMaker algorithms often support spot training. So as Samita who has mentioned how Amazon EMR can utilize spot instances for savings, you can also utilize that excess AWS capacity for your SageMaker training jobs as well. The particular logs of this training job are also visible through the CloudWatch interface if your particular organization utilizes that service. So I can actually go to the SageMaker interface on the console while this model is being trained. And on the left-hand panel, you'll notice there's a drop-down for training. I can go ahead and select training jobs. And we'll see this particular deep AR electricity demand as we named it is running. And in fact, it has actually completed. From here, you can see the information that was passed to this algorithm training. We can see the instance type and the instance count that we had specified. We can see the S3 location of the input data. We have various metrics that were captured throughout the training process, things like the root mean squared error and the loss, as well as the various hyperparameters that we had submitted to this job. If I go back to the notebook, we should see that this has completed as it has, and we can see that there has reported a training seconds and a billable seconds to the user. The reason being for both of these numbers is had we used a spot instance in this situation, the billable seconds would be some fraction of the training seconds to show the amount of savings that the end user received. Now that we have built this machine learning model, let's go ahead and utilize it for some probabilistic forecasting of electricity demand. We're going to use the final month of our training data, December 2013, as the input to our testing model. Again, remember this algorithm looks back at some data and then predicts the next future data. So we will get the following January week as our tested data. We're going to utilize our cluster one last time in order to prepare that data set for which we want to run inference on. Go ahead and run these cells here, and then go ahead and write that testing data set as our batch transform input. You can see that the data is writing. And then we'll go ahead and utilize SageMaker model hosting in order to generate the outputs. SageMaker supports several different model hosting techniques, one of them being real-time hosting as a 24/7 RESTful endpoint. For this particular use case, we're going to use what is known as batch transform or a transformer. What this does is it simply takes a portion of data from an S3 bucket and it runs the model across all of the data, which is what we want to utilize here in this example. Similarly to the training job, this transform job will run as an ephemeral job where you're only billed from the start of the transformation to the end. Currently, we can see that that instance is launching, and we'll also be able to receive the logs when it is completed. While that runs, you can take this moment as a time to catch up if we have fallen behind a little bit, but also I want to look back now at our clusters tab. Here you can see the visible clusters for my user, and if I go ahead and click the refresh tab, we can now see that my new cluster that I launched in the beginning of this session is available. If I were to look at the create cluster tab, the cluster had been successfully created, so I can close that as well. So we now have two different EMR clusters for which I can connect to. And in particular, this my new cluster will actually spin down after 2 hours of idle time. If we go over to the AWS console at this point, we can actually visualize this batch transform job under the inference tab. If I click the inference tab, I can look at batch transform jobs, and we will actually be able to see this one being in progress. Again, here we have the information that was passed to this particular transformation job, the instance types, the instance count. These can be parallelized across sharded S3 buckets, as well as various environment variables if we had passed any of those and things along those lines. After this transformation has been completed and we have performed our future predictions of the electricity forecasting, we're going to visualize those results along with their predicted probabilistic intervals. Now that we have finished our model transformation, let's go ahead and visualize the results. Going to run this plot function for which we will utilize the percentiles of the probabilistic forecast on a random client choice. Here we can see that the actual values and the predicted values are slightly differing at some of these high points of electricity demand, but overall we can see that there is a trend within these percentile predictions. If I run this cell again, I will get a different client due to the kind of random choice here. And some of these are better than others, as you can see. In this case, the predicted values kind of follow the same trends of these actual electricity demand values, and kind of the higher actual values fall within the most extreme predicted probabilities. I hope you've enjoyed this lab. You can run the final cell to clean up your connection to the EMR cluster. And going forward, if you are following along with this lab in your own AWS account, you could either shut your EMR cluster down now or wait for the idle timeout to complete. Thank you all for your attention in today's virtual workshop. Again, my name is Sean Morgan, and looking forward to working with you all.